Okay, so this is the problem. First of all, what is this thing?
The initial rate of consumption of A.
Which consumption? Is it? Yeah. So why is that important to point out the initial consumption versus just consumption? Yes. So this is a common way to gather kinetic data is you do initial rate analysis. You look at just what is the rate, again, if this is a concentration per time and it's going down like this, I take this initial slope. And that is the initial rate of the reaction. And the reason why that's a useful thing to do is it allows us to treat the system sort of much more simply by just looking at what are my initial pressures, which we know what those are. That's what we set. Okay, so how do we solve this problem? It says what species are on the surface? What does B tell you about the reversibility of what's absorbed? Derive a rate law. How would you plot your data to linearize the initial data in figure A? I don't know if I assigned E or not. Something about what are the adsorption constants for A and C? Or it tells you the adsorption constants for A and C, and it asks you to calculate the number of A and number of C adsorbed, which isn't that hard, actually. Yeah?
So you want the rate, like what each one says?
Say that again?
So you want what each graph basically tells you?
Yeah. I mean, that's what technically it asks what species are on the surface, but I think that's the better way to describe
A
it.
and C?
A and C, what?
Because there's no dependence on B. If you change GP, there's no reaction rate changes to C. Right?
Okay, so let's say if B was on surface, if the coverage of B was greater than 0, what would happen? Remember that B is a product. So what would happen to the rate as I change the pressure of B? Would it go down or would it go up? The net rate would go down, right? Because either the reverse reaction is taking place, which would decrease the rate of consumption of A, or B would simply be blocking sites, which eliminates the availability of sites for A to do chemistry. So that means theta B is equal to 0. So how do we then know that C is on the surface?
The reaction rate is going down. So in the rate law, it has to be in the denominator.
But what if it's just because this is a reversible reaction? What if putting C in there is just driving backwards the reaction and therefore...
No, I think the mechanism is C binds to the catalyst and then B comes into the gas phase and clumps with C, basically. So B never absorbs, C does, but B needs to come in and bump with C.
Well, let's back up a step. I shouldn't have put equals 0. Just because you can't sense inhibition doesn't mean that B is not adsorbed. Imagine, for example, that over this range of pressures, we went from a coverage of 1 in 10,000 to 1 in 1,000. That's perfectly normal, in fact. So just because you can't detect something on the surface doesn't mean it's not there. Doesn't mean that it doesn't react as a bound species. It simply means that it's never present within this range of pressures at a coverage that is sort of noticeable to the reaction. Because what would happen, right? This would change the rates by an extraordinarily small fraction. You wouldn't be able to notice the shift in rates. Because you took away 10 in 10,000 sites. You wouldn't notice that. So this doesn't mean that theta B is literally 0 at all conditions. It just means that the concentration of B on the surface, or the coverage of B, if you prefer that, is very small. And again, it only tells you about what's true at this range of pressures of B. It doesn't tell you anything about at all conditions. Okay, so going back to C, how do we then know that it's not, that the reason why C doesn't decrease the rate is because, yeah?
It would have to react with B and make the reaction go backwards, and not like just intermediate by swapping stuff.
But again, B is available. Just because it's present in low concentrations doesn't mean it can't react. Because it's the initial rate. That's certainly valid if I'm far from equilibrium at the initial conditions. Right?
I argue that like it's not really that reversible because it's more likely that it's going to favor the product side because you have gas being formed, as it's written here, you have gas being formed from the surface sites.
I'm not sure what you mean by there's gas being formed from the surface sites. Well, this is the overall reaction. It takes two gas molecules, it makes two gas molecules.
Right. But we're talking about like, we're trying to speculate about the mechanism, like what's attached to the surface and what isn't. We've established that B is not on the surface.
Yes.
Ergo, A must be attached to the surface to carry out the reaction, right? And it's
No.
producing B.
There's nothing wrong with saying, now again, this data wouldn't support it, but
Right.
you can have a system in which there's no A on the surface, there's no B on the surface, there's no C on the surface.
Right, but then why are you using a catalyst?
Plenty of reactions take place that way. All it means is that once the species react, or once the species absorb, they react very, very quickly. So they never really build up a large amount of them on the surface. The surface is always essentially bare, in fact, because it's so reactive, that as soon as something sticks to it, it can easily continue to react and leave. So, I mean, there are many catalytic systems that operate under very low coverages, especially depending on the conditions that you're at. Yeah?
How could you do that for a reaction that isn't unimolecular? Because how would you, if you don't have high enough coverage, how do you have a high enough rate of things being close enough together to interact?
Because species can move on a surface. Species are not fixed. So if they're moving very rapidly on the surface and they run into each other and react, then they're happy. And you can do that chemistry at low coverage. Or you could just be at really, really low pressures. I mean, that, that's part of surface science. So they run at ultra high vacuum conditions, and their surfaces are fairly clean when they do chemistry. Yeah.
Kind of a bio-lab, but like, if the reaction is B plus C, then if it were reacting, would its rate be linear? Well, if it was elementary, you would say its rate would be linear with C, but I don't think I can say that. So I'm still trying to figure out like why we know it's not just.
Oh, you're saying that the rate of the reverse reaction should be first order in C? Yeah, I mean, you're right in the sense that that's kind of risky to say if you don't know that the reaction is occurring by element, if you don't know the elementary steps involved. C or A?
That was kind of like the crux of my whole argument is that like what you're saying was obviously correct, but like it doesn't make sense in this context because obviously it depends on the surface concentrations in this context according to the graphs. Right? Like
All right, so let's look at this one then. So what's happening over here?
It's increasing at low concentrations, like parabolically.
Right. So we know that the rate depends on the concentration of A in the gas phase, but that's not surprising because that's the reagent. What does this look like? Yeah, so this looks like at low pressure of A, the rate of A is proportional to the pressure of A squared. Again, maybe not that surprising because there's two of them here. Then what happens when I'm at this regime? Am I at equilibrium, or is my coverage of A equal to 1?
It's saturated.
How do you know? How do you tell the difference?
Because this is the initial reaction rate we're dealing with, right? So it's not, this is at time t equals 0. Put in all of A, and some of it has to bind to the catalyst for a reaction to take place. RA would be 0, right? If it were, RA naught would be 0 for ready. Well, RA net would be 0.
Yeah, but that is RA naught. I mean, that's what you measure is the net rate.
Okay.
So what if I'm just feeding in the equilibrium pressure of A?
But if that was the case, it would never react to the
Still
first
having
place.
product.
No, so I mean, you're on the right track. this would only go to 0 if you're at equilibrium. The fact that it's not changing doesn't mean that you're at equilibrium. The rate is non-zero. I think that's what you're trying to say. I kind of jumped over your head there. So if the rate is non-zero, I know that I'm not at equilibrium, right? So the reason why this becomes flat is because at this condition, the coverage of A is 1. So again, that means that we know that A is on the surface. We know that B is not. That this is not a kinetically relevant adsorbed species. In fact, there's a term, it should be in the book, but I'll make sure that you get it before we're done. And now what happens with C, though? First of all, is there any correlation I can make between these two plots? Does this mean that just because it's on the right side of the plot, does it mean that I'm here? No, right? Okay, just making sure. The x-axis is totally different. This tells me the pressure of A, but unfortunately this doesn't have numbers on it. So I don't know if that